Welcome to Advanced Reverse Engineering. We're going to talk about Python, which is a programming language we'll be using, PyElfTools, which is a Python package for working with ELF files, which are the binary files on your system, and Capstone, which is a Python library for doing disassembly. So let's start by talking a little bit about Python. A lot of you probably already know Python, and that's great. If you don't, I don't think you should panic. It's not hard to pick up the Python language. Really, it isn't. It's a language where it's very easy to get the basics pretty quickly, I think. Parts of it can be a little tricky, but I think you can pick it up pretty quickly overall. So one of the things you might do is run that top command over on the right hand side. Right now at the prompt, if I type Python, it complains. So what we want to do is we want to say Python is Python 3. And now it knows that Python is Python 3. A similar token, you can install IPython. IPython isn't really a different interpreter. It's a module that you can run on top of Python, and it provides sort of an enhanced and more interactive Python. So Python is very interactive already. You often work at the prompt to do stuff with it. IPython just provides a little bit nicer prompt to do that work. And you can install it with the same thing. Sudo apt install. It'll go out and find the things it needs and get them. And then you'll have a little bit nicer prompt to work with. When you want to get out of Python, quit with parentheses will get you out. Quit's a function, so you gotta have parentheses. Or you can just type Control D. Control D is end of file, and that will take you out. So Python is both an interpreted and a compiled language. The Python compiler produces bytecode, much the same way that Java does. And you'll know you're looking at Python bytecode when you see a .pyc file lying around. So the normal extension for Python scripts is .py, but they can be compiled and cached by the Python interpreter and hidden away, and then loaded when you are ready to use them, and they run faster. A basic template for what a Python script looks like is over on the right. So up at the top here, I've got a little shebang followed by user bin env and Python 3. So what is that? So if you're not familiar with it, user bin env, I'm not going to go into all the details of it, but if I just put something at the end like Python 3, you see what it did. It ran Python 3 for me. And what this is doing here is it's preventing me from having to know where Python 3 is installed. As long as it's in the path, this will find it and execute it. So I don't have to have the absolute path to it. I can just say user bin env and Python 3, and it'll go find it in the path and execute it. Python's big on documentation. Documentation strings in Python occur at the start of functions, at the start of classes, and at the start of modules. Well, I'm in a module right now. Every Python script is a module. And so here, with 3 single quotes on either side, I have a string. And Python knows that when you have a string like this, it is providing the documentation for that particular module or function or class. You don't have to have it, but it's a good idea to put it there. And the nice thing about the 3 quotation mark strings, and they can be single quotation marks or double quotation marks, is that they can span multiple lines. So you can have a long comment up here inside these 3 quotation marks pairs. So lots of stuff goes in here. Then typically at the bottom of your file, if it's a file you intend to just run from the prompt, you'll have something like this. So a Python script can contain a library, effectively. It can define functions and classes and that sort of thing, and can be used for that effect, right? I can incorporate that. I can basically include it in my program, and it'll provide those functions and classes. But sometimes I actually want the script to do something. I want it to run some code. And so what I'll do then is I'll have something like the following. I'll check to see if the current name is main, and if it is, then I will go and do some actual work. Often what you'll do here is you'll call a main function, or you'll call some other function to kick things off. Here I just said, hello Python world. This is a complete script. You can put that in a file like template.py, and you can run it. And you can run it in a number of ways. You can say Python 3 followed by template.py, or you can make template.py executable through using chmod. So you'd say chmod, change mode, plus x, making it executable, template.py, and then you'd be able to just run template.py. If you're curious how things get compiled and where the compiled stuff ends up, here's your flowchart for that. If it looks crazy and bizarre, it's a little crazy and bizarre. Dynamic typing is part of the Python language. That can be super convenient, or occasionally it can bite you. So you see up at the top, we say A is 5, print A, prints out 5. Nothing remarkable there. These 3 greater thans are the Python prompt, by the way. So then if I say A is 5 in quotation marks, and I print A, I still get a 5. If I ask what the type of A is, it tells me it's a string. Alright, I can also do some static typing. So here I say A should be of type int, and then I assign it a string. And you might think any reasonable programming language will know that an integer is not a string, and it will complain. Python doesn't. The type that you have here, the :int, that's a type hint. Type hints aren't enforced by the language, but they can be used by a type checker to type check your program and guarantee that it's soundly typed. But that's an extra step that you have to run. You actually have to invoke the type checker to do that. Otherwise, it's just a hint, and the interpreter is free to ignore it. So if I type out the type of A, it's still string. I can import the math package. This is how you bring a new package in with import. And now I can ask it what the square root of 5 is. It'll give me an answer. I can ask it what the square root of A is. What is A? A is a string, and what I'll get is an exception. And a Python exception comes out looking like this. In this case, it's a type error, and it says it must be a real number, not a string. Okay, good. Here's an example of some static typing. Typed.py. So up at the top, I have the little line to start Python 3. I have a documentation comment here. I import a module called sys. Sys is handy because sys lets me get access to my command line arguments. So down here at the bottom, I check to see if name is main, and if it is, I run a function called main. And up here you'll see this is where I've defined the main function. And the part that's necessary here is def. That's how you define a function. You say def, the function name, and then parentheses with the arguments, or I should say the parameters, inside the parentheses. If you want to provide the return type, and again it's a type hint, it can be ignored by the interpreter. You do that by giving an arrow and then the return type and a colon. So blocks in Python are formed by indentation. So you see how this is all indented over here at about the same level. That's what you want. The colon indicates that you're starting a new block, and the indentation is how Python knows what's in that block. There are no curly braces at the start or end. There's no special token at the start or end to indicate that. It's done by indentation. Here you see an if statement. If the length of the argument array is not 3, colon, and then I have an indented block here that's run when that if is true. So the argument array works much the same way it does in C. I don't have argc, but I can ask what the length of the array is. And I expect the 0th element to be my script name. And then I want to have 2 other arguments. So I really want this length to be 3. And if it's not, I'll say you must supply a number and a string as arguments. And then I will do a return 1. You can also do an exit. But exit is a function in a module you have to import. Return is the easiest thing to do. I just return 1 to indicate something went wrong, and I'm done. So there you go. I didn't mention it, but there is a documentation comment at the top of this function. So then I have times, and I'm going to provide a type hint for it. I'm going to say I want it to be an integer. And what is it? Well, I take sysargv1. That's going to be a string. How do I turn a string into an integer in Python? Well, I just wrap it in a call to int, and what I get back then is an int. I've constructed a new int from this string. The second argument is meant to be a string, so I just say string :stir sysargv2, and then I do a for loop. And the for loop says for index in range 0, times, colon, and then there's my block. I print string every time. So, and so there's my block. I print string every time. So range is going to produce all of the values from 0 up to, but not including, times. And index is going to iterate through them. And so this is going to run times, and it'll print out string each time. And I'm done, so I return 0. You could drop this. You could drop the return type for the function. You could drop the types for times and string. And this would go through just fine and run and do its thing. To check this, you would need to use MyPy. Now, MyPy is not yet included by default, but you can install it using apt as well. And now it's installed. So now with MyPy installed, I can try to check that program. And I have it lying around here. There it is. So we'll check it. And it will say I didn't find any issues. The typing looks correct and consistent to me. And that's great. So if you want documentation on type hints, you can find it there. And I think type hints are great. I think I want the compiler to help me as much as possible, and types are a way for it to provide more help. If you don't want to fool with it, you don't have to. It's an optional thing. Another optional thing that I think is super helpful is lengths. So you can and should use a linter. PyLint works really well. So we'll install Pylint. And it provides you with a lot of guidance about the way things should be done in the language. And you'll see it says, hey, your code was rated 8.33 of 10 because you've got some weird stuff here that I don't like. On line 21, you've got some trailing new lines. On line 15, you've got an unused variable index, and that's weird. So we can take a look at that. And sure enough, there's an extra new line at the end we don't need. And I think it was 15, was it? Yes, index. So index is never used in here, and so we don't really need to declare it. Instead, we can use an underscore. And now, Pylint is quite happy. It rates my code a 10 out of 10, and it's still going to work. The underscore, you put an underscore in front of a variable name, and then Pylint will know that you don't necessarily mean for that variable to be directly referenced. Again, it's going to give you lots of good information. You can use the strict flag with it to get even more linting. Good stuff. So as I said, you define a function with def. Colon introduces a body of a function or a class or an if-then-else or a while loop, any of those things. Any place where you would expect to have the curly braces, you instead are going to have a colon and then an indented body. Okay. Something of interest over here in this simple little function called function.py. So I come in, I check to see if I'm in main. I check to see if my argument array has at least two things. If it doesn't, I say I'm missing names. If it does, then I go through the list of them and I invoke hello for each one of those arguments. What does hello do? Here's hello up here. It's a little function. It has a documentation string that says say hello to the argument being name. And then I print this out. I print F, double quotes, and they can be single quotes too. Hello, and then name in curly braces. This is an F string. Okay? An F string is a formatted string. The Python interpreter is going to see this, and it's going, this F, and it's going to go through the string and look for things like this name in curly braces. And when it finds that, it's going to replace name with the actual value of the variable name. And there are formatting options for this, and you can have expressions in here. It's really very nice. Another thing to notice was down here when I said for who in sysargv 1:. What's happening here? What's happening here is the 0th element of argv is the program name. I don't want the program to say hello to itself. I only want it to say hello to the different arguments. And this is a way for me to provide a slice of an array. So argv is an array. I referenced it into it with square brackets. And what this says is start at offset 1 and then go to the end. So I could have an index here and an index here. But since I just have one at the start, it's going to run from 1 all the way to the end, skipping item 0. So F strings are super useful. I recommend you go and read about them. They will be really handy. Documentation, I've been mentioning all along. Documentation for the module, documentation for functions, classes. All these things can have a string just sitting there at the start of them. Usually you'll put it in 3 quotation marks, double or single quotation marks. And that will provide documentation for that particular thing. And Python can use that documentation interactively and provide it to you later. So Python is really big on documentation, and it will provide access to this documentation to you at runtime. You should always write some documentation for your stuff. So let's go down here, and let's start up IPython 3. And let's ask it for help. and it says, hey, you can use help for interactive help. Well, let's try that. There we go. Welcome to Python 3.10's help utility, and type the name of any module, keyword, or topic to get help on writing Python programs and using Python modules. Well, that's interesting. So we just enter something like def, and it will tell us about def, and it uses a pager so we can walk through it. Hit Q to stop. I can also ask it for help on particular objects, like, what about help on 6? Well, I'm in the help utility, so let me pop out of that and then type help on 6. There we go. And it will give me help on integers. And again, I can page through them and hit Q to stop. What about strings? Well, that's not going to work. Python doesn't do it that way. It will complain, but it will give me useful complaints. It will say, you should use help str if you want help on strings. And now I have help on strings. And that's good. You're going to use this a lot. It's going to be super helpful and super useful. And I highly recommend you make use of it. A few other things. So you saw that when I did help on 6, it started providing me with lots of information, methods, and such. I can get a shorthand for all of that by using dir. That will show me a list of all the attributes and functions that are part of that particular thing. And then if I see one I like, I can go and ask about it. And it will then tell me about, in this case, 2 bytes, and I can find out what that does. So it's a great utility. I really recommend that you make use of it, get familiar with it, and make use of it. So here's some discussion of that. If I import, let's say, a function from the previous thing, and I say hello Fred, I got hello Fred. If I do a directory of that, you'll see that there's a bunch of stuff that's provided for me by Python. It provides stuff like the file and other information about it. And you can see hello and sys are also in there. So I can say help, for example, on this function, and it will give me some help on it. And you can see it's taken my doc strings and it's put them in here so that I can see what's happening with it. Basic operations are simple. A single slash performs division, and it will produce a real result. So 5 divided by 2 is 2.5. If you want integer division, truncating integer division, you want 2 slashes. So 5 divided by 2 is 2, because the floor of 5 divided by 2 is 2. How about this? What if I say 5 divided by 2, right? And I get 2.5, but I wrap it in this integer thing. Well, it's going to truncate it and give me back 2. Likewise, I could take the integer division, 5 divided by 2, wrap that in a float, and now I have 2.0. I could convert it to a string by wrapping it with stir, and now I have the string, 2.5. I could take an int, which I produced from the string 5, divide it by a float, which I produced from the string 2, and I'll get 2.5. And you can see here that I can use mixed types. Python is very liberal about how it interprets types and what you're doing. If I want a hexadecimal number, I can just say hex. In this case, I want one for 10, and it will give me 0xa, and note that's a string. For binary 10, it will give me 0b1010, right? That's 8 plus 2, which is 10. And I can use hex and binary literals in Python as well with a 0x or a 0b. And you see here what I've done is I've said I want to take 0xff, add 1 to it, and convert that to hex, and then interpret that as an integer in base 16. So that was a lot. So what's going to happen is this is going to produce a value, in this case 256. I'm going to turn that into a string, a hexadecimal string. So that will be the string 0x100. And then I'm going to turn that back into an integer until it's in base 16, and I will get back finally 256. Now this string is going to begin with 0x, so it should be possible to infer that the base is 16, and in fact if you set base equal to 0, it will do that. It will infer that the base is 16 and just print 256. Some other basic operations. Exclusive OR is the caret. So 3 exclusive OR with 3 is 0, and 3 exclusive OR with 0 is 3. The remainder operation is the percent. You can also think of that as the modulus. Exponentiation is 2 asterisks because the caret is used for exclusive OR, so it's 2 asterisks. 5 squared is 25. And 5.0 squared is 25.0. So you see how it tries to deduce the right types for things. 25 to the power of 0.5 is 5.0. And I can also take a string and I can wrap it in an eval. And in this case, I take the string 6 asterisk 5, I eval it, and I get 30 because 6 times 5 is 30. If statements are pretty simple. Here's an if statement. If value is greater than or equal to 21, pass. Pass is basically a placeholder in Python. It allows you to have a non-empty block that's indented. So if the value is greater than or equal to 21, don't do anything. Else if, and the way you write else if in Python is elif, the value is greater than or equal to 10, say it's at least 10. Otherwise, if it's greater than or equal to 5, it's at least 5. Otherwise, the value is too low. So if, elif, else. And of course, because we're using indentation for the blocks, there needs to be nothing at the end. We just don't indent. Loops are pretty simple. You saw the for loop earlier. Here's another one where I have the range with a stride. So I say for x in range 1 up to but not including 10, and I want to count by 2s. So I would start at 1, and then I would add 2, and then I have 3. I would add 2 and have 5, and then 7, and then 9, and then I would add 2 and I'd be done. I would never get 11, right? Because I stopped when I hit 10. So I could print each one out. And a nice thing about loops in Python is that they're allowed to have an else. So as long as this loop predicate is true, it's going to print x. When it turns false, it will print done. And so I get 1, 3, 5, 7, 9, done for this. If you're wondering about the 3 dots, when you are at the prompt and typing, you have this greater than as the prompt, and you type a partial statement indicated by ending it with an open parenthesis or something like that, or in this case a colon. Python will prompt you for more stuff with the 3 dots. And so I'll enter that. I enter the unindented else, but it has a colon, so Python knows more is coming. It prompts me again with this, and then it prompts me with this, and I'm done, so I just hit enter, and then it executes the thing that I've typed in. Up here at the top, I set a equal to 13, and I say while a is greater than 10, print a, and then subtract 1 from a. So a minus equal 1 will subtract 1 from a. You might wonder if I couldn't have just said a minus minus, and I can't. That's not in Python. But a minus equal is, and so I'll get 13, 12, 11. Exceptions. Python has exception handling. Here's a little demonstration of it. You can see, here's my main function. I'm going to check a length, give an error return. Then I try to do some stuff. And in particular, I try to open that name I was given as if it's a file reading text. So I want to read text from that file. Now, something could go wrong. A number of things could go wrong, right? I might not have permission to open and read that file. I'll get a permission error. That file might not exist. I'll get a file not found error. Something else might happen, and this is a catch-all exception here. And if none of these exceptions catches, I can have an else. In this case, I'll use else to close the stream. And I can guarantee that at the end, a finally will run. If nothing else takes me out of the program, this finally will run, and it will print done, and then I'll return 0. So try, except, else, and finally is a pretty comprehensive way to deal with this. The finally block is always executed. The else block is executed if there are no exceptions. Otherwise, the first matching exception is executed, and if none match, you can have a general catch-all that catches all the exceptions. If you want to raise an exception, you say raise, and then you give it an exception to raise. So that's pretty much that. Classes are really very simple as well. So here is a class. If you've done any Java programming or C++ programming, you're aware of the concept of a class. A class is a template for making objects. And here's one. This class is called greeter, and it has a docstring, and it has a number of methods. And there is one that we'll come back to in a moment and talk about, and that's init. But you can see get greeting and greet take a self as their first argument. So self will be the actual object, an instance of greeter that you're being passed. And so for get greeting, I will take self, I'll take a name argument, and I'll return my self greeting plus a space and name. And then for this one, I will actually print it out. So get greeting will return a string to me. Greet will actually print it out at the prompt. How does self greeting get set? How do I get back a new object? Well, that's the job of underscore init. So to be specific, a class has a new method, but you very seldom have to deal with that. Normally what you want to deal with is the initialization of the data in the instance, and that's what init does. So I'll call new. The default new will make an instance of the object for me, and then we'll turn around and call my init method and pass that instance to me, which then allows me to set, in this case, I set an attribute on self to be the greeting. And I can just do that. I don't have to have it declared anywhere. And there you go. If you want to override new, you can do that and do all kinds of neat stuff. I'm not going to go into that right now. You can have class methods. A class method wouldn't have the self here. It would actually have an instance of the class here, which is usually written CLS. And you indicate a class method with this at class method decorator. So I'd put it right in front of the def, at class method, def, and then I would have a class here. You can also have static methods, just like you do in Java and other languages, where you don't have an instance to worry about. A static method is indicated with the static method decorator. And so I'd have static method before the def, and I wouldn't have a class or a self here at all. It would just be an ordinary function which happened to be inside the scope of my class. You can add variables to an instance. You can add variables to the class. All those things are possible. How do I add a variable to the class? Well, I get the class instance, the CLS thing I mentioned earlier, and I just set an attribute on it. All right. That's Python. If you don't know Python, take a little bit of time and learn you some Python. Once you've done that, then come back and let's work on the next thing, which is Capstone and PyElf tools. We're going to be working with binary programs. The binary programs are stored in ELF files, and they're in machine code. So if we want to be able to work with it, we need to be able to decode what's in the ELF file and then be able to disassemble the stuff that's code that's present in there. And that's the job of these two packages. So PyElf tools is a pretty neat little tool for manipulating ELF files. And the way to install it is typically to use pip. The way you normally do it is to use pip. So I'm going to pop out here and I'm going to say pip install PyElf tools. And it's going to go ahead and install it for my user. Now, I'm not presently on Ubuntu. I'm on a Debian derivative that's not quite Ubuntu. Some have gone to preventing you from using pip directly, but they will, if you try pip, they'll say don't use pip, don't do that, install stuff this way. But if you have to use pip, then use, and I think they call it xpip or something like that, just use that and it will work pretty much the same way. So PyElf tools is now installed. And then the next thing we'll do is test it out. Let's try it out. So at the prompt, you'll type Python or IPython3, and then you can begin to play around with it. And if you have a little bit of experience with Python, this will all make a little more sense. So at the Python prompt, or the IPython prompt preferably, you can just sit and just interact with it and play around with it. You can get help on stuff and work with it. Over here on the right hand side, there's a little script. The second line is worth mentioning. You'll see that I import something called ELF file. That's one of the main things I'll be working with. And I import it from here. So this might look to you, if you're a Java person, like a path to a particular module, and that's what it is. So I can just say import ELF tools, and that will work. And now ELF tools is in the scope, and I can reference things by giving the dots and all the pieces. Or I can go and get what I want out of that particular package, and I would do that by saying from ELF tools ELF file import ELF file. One of the nice things about IPython is, as opposed to a regular Python prompt, is that it has auto-completion. So I could say from ELF, and I type and it hit tab, and it gives me ELF tools dot, what have I got? And it gives me a list of things, right? Common, construct, dwarf, module, ehabi, and ELF. Well, I want ELF. So I'm going to say I want that. And I'm going to hit tab a couple more times. And I get a whole bunch of other stuff here. And I want ELF file. And so from there, I want to import ELF file. And you can see it's still doing its auto-completion thing. I do that, and now I've successfully imported ELF file. What's in ELF file? Well, help will give me a little bit of information about it. And you can see that it's a class. And to construct it, I give it a stream. And the constructor accepts a stream, a file-like object, with the contents of an ELF file. Optionally, a stream loader function can be passed. Fine. Accessible attributes, the stream itself, the ELF class, 32 or 64, right? It's going to be 64 in our case. Whether it's Little Indian, it will be in our case. The ELF type, the header, etc. And then there are methods defined in here, and we'll go ahead and start listing out several of the methods. And get machine architecture, get section by name. Oh, that sounds really like something we'd like to be able to do. Get section by name. Great. Let's pop back up here and let's see what we did. So here we go ahead and make one. I go ahead and open, in this case, user bin ls, reading it as a B for binary file. This is important. By default, you're reading text files. You don't want to do that. You want to read binary files. So use a RB here to indicate binary. And again, I'm using single quotation marks, but you can use double quotation marks as well. They're interchangeable in Python. So we're going to open user bin ls, reading as a binary. So I'll just say ls file is going to be open and user bin ls. And there we go. And if I'm curious about what's going on with that, I can say help ls file, and it will tell me that what it is a buffered reader. In other words, it's a thing that reads and has a buffer behind it. And it'll tell me some of the things that I can do. I can get the underlying file descriptor, I can flush it, and I can peek at it, and so on, and read from it, etc. I don't want to do any of that. What I want to do is use that to build an ELF file, and that's pretty easy, it turns out. I just say ls_elf is ELF file of the ls file, right? I provide it with the stream, and that's what this is. And now I have initialized my ELF. You can try to print some of these things out too, and it will tell you a little bit about what they are. In this case, it tells me that this is an ELF file, and it gives me its location, which is not maybe the most helpful thing. So now that I've got that, I can go and use that method I wanted to use, get section by name. I like the idea of that. So let's go ahead and say ls_elf dot get section by name. There it is. And let's use the name text.text. And you'll see it returned to me a section. But I didn't bother to save it. Oh no, why didn't I save it? It turns out the most recent result that you get back is available to you in the little underscore variable. So I can now say ls text equal underscore, and I've captured that. And again, I might want to know what that does, and this will tell me about it. It turns out I've gotten a section. That's great, it's a class, and it has lots of properties, and it has some information in it, like the data size, the data alignment, and the data itself. Data sounds interesting. Let's see what the data looks like. Is data, what is data? It's a little method we can call. Let's just do this. Let's see what we get. Wow, we get a Python binary string. So all these little guys, like this guy right here, that is 255. There's lots of these. Some of them are printable, like H here, but most of them are not. So you can see that what's happened is, this is what you would expect. I got out a bunch of raw stuff. So that's neat. I can just say code equal oops. Let's do this. There. And now I have all of that in code. How much is there? About 75K or so of bytes. Ready to be disassembled. What else can I find out about the section? I thought I had a, I can't find it. Let's see. Help ls text. Size, directory. So I can find out some other stuff about it. Right? I can find out the section type. I can find out whether the section is null, whether the data has been compressed, what the data size is, etc. We can also get the headers. So, for example, I can go and get the headers for that. What did I call it? I called it ls text. So there is the header. These little guys are the defined names for the different pieces of the section header. Where can you find out more about them? You find out more about them here in the man page for ELF. Right? So if we go and find information about sections, there's section header right here. You'll see that we have a section header name, type, flags, offset, and so on. And in fact, that's what we see here. So it's exposed to us in a way that makes good sense. And what's interesting about this header information? Well, let's go there. Well, one thing that's interesting is this, the address. So what is this address? This address is the address that was assigned by the linker to the text section. So if I'm looking at the 0th byte in my little data thing that I've gotten back from the text section, the 0th byte would be at this address. And if I find the 11th byte, I would take the 11 and add this offset to it, and that would give me the address of it. Hope that makes sense. So there you go. There's some other stuff that you can poke through here to learn more about it. For example, you can look for the entry point. If I go back to the ls elf, that was the thing I created up here, the elf file. It has a header, and I can look at the E entry in that, and that will be the entry point. All right. That takes us to Capstone. We install Capstone the same way. I'm going to pop down here. I'm going to install Capstone. And now I have the Capstone package. What is Capstone? Well, Capstone is a disassembler engine for many different platforms and architectures. And we're going to use it to disassemble x86-64 machine code. So we do the same thing. We can play with it the same way. The way that you do it is you create a disassembler object. And if you look over on the right, you'll see that we do the same kind of thing we did before. From Capstone, we're going to import a couple of things, CS and CSINSN. What are these things? Well, this is the Capstone's disassembler and its options and so on. And this is the Capstone instruction. This is a particular instruction. So then I'm going to import the x86 architecture and the 64-bit mode. And so now I can create a disassembler using my little CS guy for x86 64-bit. And yes, you can create it for other ones as well. ARM is in there, 32-bit stuff is in there, etc. It's a very nice package for that. And that gives me back an object, which I'm going to save as dis. So let's go and do that from Capstone import CS and CSINSN. From Capstone import CS and CSINSN. We also wanted to import those two constants, CS arch and CS mode. And there's a lot of them. We want CS arch x86. Right there it is. Boom. And we want CS mode. And there's a bunch of those. But we want this one. Again, IPython and the autocomplete, really helpful. So now that we have those two, we're going to make that disassembler by just calling CS with those options. And we can, of course, ask for help on the disassembler, and we'll get it. We'll get lots of information about the disassembler. What can we do with it? Well, the disassembler has a disasm method where we can provide it with some data and a starting address, and it will then give us back instructions. That sounds like something we should know about, right? Sounds like data and, right? Because this was the data we got back here, right? We got the data from the text section. That's that data. And this tstart, that would be the starting address. And we got that from the header right here. Tstart text header shaddr. That's where we got that. Given those two things, it's now possible for it to begin to do disassembly. And INSNS here, the thing you get back from this, that is an iterator. And I can call next on an iterator in Python. I can use a for loop on it or a while loop, etc. But if I call next on it, I'll get the next one out. That's a single instruction. And now that I have a single instruction, I can do things like print its mnemonic and print its operands. And you can see here it gives me back a particular disassembled instruction. So I've managed to go from nothing to being able to open up an ELF file, find the text section, and extract the address of the text section and the data in the text section, and then use Capstone to begin disassembling the data in the text section. All right. I think that's enough of that. The thing that you need to do now is to do it yourself. And we'll get back to that in just a moment. There are a few things I wanted to cover because I've seen people struggling with this, and it bums me out to see you struggling with this. So we're going to go over this and hopefully put this to bed. I think for a lot of you, probably most of you, this is not an issue. But for a few of you, I think you're still struggling with this. And there's two kinds of complexity in the world. There is essential complexity, right? Something is hard because it's actually hard, right? Assembly language is hard because it's actually hard. And then things are hard because of accidental complexity, right? There's nothing inherent that makes it hard. It's just that we've created a system that's unnecessarily confusing and it's causing things to be hard. So we want to focus on the essential complexity and try to push that other stuff, that accidental complexity, out of the way. And that's really the job of MK, but it seems like none of you have read the documentation or the help for it or the fact that there's a bunch of pages for it. None of you have done that, which is okay. That's fine. You don't have to read the stuff. No one's going to make you do it. But I figured I'd go over it just to sort of maybe pressure you into it. If you want to get it and install it, I recommend you go ahead and get the latest version. The latest version is actually not right now in iLearn, but you can get it by running that wget command right here with that link, and that will spit out a bunch of stuff and download it. And once it's downloaded, you can just say, you can just run it with bash mk.sh, and that will fire up the installer and install it. What does that look like? And by the way, it's just a text file. Feel free to read it if you want. Let's take a look at that. So we'll just say wget And what does that look like? GitLab.com. And it's raw master. And there we go. Now we've got it. And so now I can just say bash mk.sh. And when I do, it will start up and say, okay, do you want to install this or uninstall it or not do anything? And what I want to do in this case is nothing. So I just hit enter and it stops. But if I did want to install it, I would say yes, and it would install. And in this case, you can see it found out that I have both a bash RC and a zshrc, and it went ahead and installed itself in both. What did it do? It added a line. So you can see right here, it's added a line to it, so that now when I run this, it will source that file and I'll have the stuff available to me. So that's how I can do it. If I want to uninstall it later, I can go ahead and run the script again and say uninstall, and it will uninstall it. So very simple. If you want the dis aliases, you can get them too. Let's go back down here, and what are those? It works the same way. Those let you do disassembly. So for example, there's disassembly of ls, and I can of course stick an M on the end and it goes to a pager. In this case, it goes to the pager bat because I have bat installed. If you don't have bat installed, it'll probably try to use most. If you don't have most installed, it'll try to use less. If you don't have less, it'll fall back to more, and I feel sorry for you. So they can be installed and uninstalled with little scripts pretty easily. So what does make do? What does make do? Make is I don't know, it's a little aggrandizing to call it a build tool. Make is just a little simple utility that does one thing. It looks for the characters mk : in the first line of a file. And if it finds those, it tries to execute the rest of the line in the current shell. And that's it. Everything prior to the mk : is ignored. That's it. So up at the top, you can see that there's the marker, the MK. This stuff over here in front of it, it's going to ignore that. Doesn't care. This is a little text file. Doesn't care about this stuff over here. Only cares about the stuff after it. All right. That's the stuff that's going to get executed. And in this case, it's ls-l. So when I say mk-ex1.txt, right, because that's the text file, when I say that, it finds that, runs this command, and I get a file listing. That's it. You'll notice a couple of things happened. It printed out the command it was going to run, so I can see what commands it's going to run. And of course, then it ran the command. Again, it's not super complicated. It's a pretty simple little tool, I think. It just happens to be handy for building assembly stuff. So just like in the shell, you can combine commands with a semicolon. So here I've got another little text file with a make at the start, and I'm going to echo $home. That's my home directory, and you can use environment variables. Basically anything you can do at the prompt, you can do here. Echo $home semicolon ls-l $which NASM. This is going to go find NASM in the path, and then it's going to print out the location. And so when I run make on this, it prints out the command it's going to do, and you can see it's already replaced home with home user, and I get the echo of home user, and then I get the ls-l of which NASM, and there it is. Similarly, files can refer to themselves. The file that the little make string is in is bound to a variable for the time that it's running, and that variable is make file. So here I have a really silly little thing, a little text file. It's got a make at the top here, and then it says cat $make file. So this file is going to print itself out when I make it. So sure enough, when I say make ext3.txt, I get the command cat ext3.txt, right? Make file has turned into the file name, and then I just cat the file out. That's what's in the file. Another example, this one's maybe getting a little bit more relevant to you. You can use all the shell stuff. You can use if, then, else, fee, and while done, and redirections, and all those things. But you don't have to know all that stuff. There's a few things that are really, really useful, and one of them is the double ampersand. Right? The only thing you can't do is span multiple lines. This only looks at the first line of the file. So the double ampersand is interesting. What that says is, if I have command 1, 2 ampersands, command 2, this says if this command runs and succeeds, and the way I know that is it returns 0, then go ahead and do this. Okay, this is, it looks like an AND, right? Do command 1 and command 2, but it's really Dijkstra's CAND, conditional AND, right? So it's a short circuit operation. If this thing returns a non-zero result, the second thing never executes. And that's really great. That's great for doing a little build pipeline. So up at the top, I have a little make here. I've commented it out so that the C compiler won't see it, right? And again, make doesn't care about anything prior to the little make, so it ignores that. It just sees this stuff after it. And so what it's going to try to do is run gcc -o and then make base and make file. And what is that doing? Well, make file is the file name itself, and make base is the file name without the extension. So this is going to be ext4.c, that's the file name, and this is going to be ext4. If this works, if GCC returns 0, it's then going to echo out success. So when I make it, you'll see it prints out the line that works, and then it prints out success. And by the way, make itself will return the value of the last command run. So in this case, the value of the echo, the return value of that gets returned. And so there you go. There's make file, which gets expanded to the file name, and make base, which is expanded to the base name of the file, or the name without the extension. If this is all, if you're wondering what all is out there, there's a debug flag that you can use. Make --debug. You give it a file. It's not going to actually run the commands in the file. It's just going to tell you about that. And the reason you have to give it a file is so it can fill in this other information for you. So here I've run on ext1 or ext1.txt, and it's told me my assembler is NASM. It's aware of a few different platforms. I do stuff on the Raspberry Pi. I do stuff on Macs and other places. And it tries to pick the right stuff. The linker it wants to use is LD. The compiler it wants to use is GCC. You can give it extra options for assembly and the linker and the compiler, and using the compiler as a linker, and those would show up here if you define them. And then for this particular file, there's the base name, which does not have the extension. There's the line that you'll be run if you used make AS, and that would be the one to assemble it. There's a line that we run if you used make LD, that would be the one to link it. If you use make DIN, that's going to use the dynamic linker, and it's a long line, so it wrapped a bit, etc. You can call make recursively. It can call itself. So up here I have a little subroutine, and then down below it I have a little thing that wants to use it. And so this guy, all it's going to do is assemble. When I run make on this, it just has this make AS, and that's going to call the assembler to assemble this file. Down here, for start, I want to assemble start, sure, but I also want to have this assembled. So the first thing I do after the make is I call make recursively on sub.asm. It's going to go out here and build this guy. And then after that, I assemble this file, and then I dynamically link this file with sub.o that I got from making sub.asm and the C library. And then I can run the whole thing. And you can see down at the bottom I do make start ASM. It prints out the big long command. That triggers the sub build, and there you go. This little guy is kind of interesting. This will print out all your environment variables. So here's an example of using this to build a static executable. Pretty easy stuff. Up at the top, I just say I want to assemble and link. Make AS and make LD. That's it. So I want to do assemble, and then if that works, link. And it's a little bit long, right? It spans over a page here. And that's it. Here I want to build a dynamic executable, a dynamically linked executable. So to do that, I say make AS and make din. Now I want to link with a few of the libraries. I can just put them right after that. So -lc and -lm. Right. This is going to expand to a command, and then after that I'm going to have these two libraries linked, the C standard library and the math library. And there you go. And this code is actually going to use those and some floating point stuff to compute the sine of 1/4 pi. Here I'm building executable and using some of the C stuff. And so you can see now I use make AS to assemble it, and then make GCC to link it using GCC. The advantage of doing that is I get the C runtime and the C standard library and all of that for free. What that also means is the C standard library is providing _start. So I'm not going to have an _start, right? Because that's already provided by the C standard library. Instead, I'll have a main, which will be called by the C standard library. And so that's what I have here. And I link with the math library still, because I'm still doing I'm doing the same kind of thing here. All right. I hope that helped. I include these things in all these little programs. You should be building this stuff, playing with this stuff, tinkering with it, finding out how it breaks, telling me how it breaks, so that we can all make this stuff better. So there's homework. You've been homework free for far too long. Let's get you some homework so that you can feel better about yourself. Homework's due in a week. And for this homework, you're going to write some Python, and you're going to use PyElf tools, and you're going to use Capstone, and you're going to disassemble a file. So here's what you're going to do. You're going to do the stuff we saw earlier. You're going to locate the file, open it up, find the text section, and then disassemble all the code in that text section. I want you to name your file disassemble.py. It should take one argument, a single argument, which is a file. Your output should end up looking like this. This is pretty easy to generate. Please make it look like this so we can automatically check it. Right, I've got a full address here. I've got the mnemonic and the operands over here, and 2 spaces. I'll format some of this stuff away so it's not a problem. But the closer you get to this, the easier it'll be for my little thing to check it. And again, I'll clean this up before I check it. Watch for exceptions. Some obvious ones are file not found error. There's an is a directory error that you might watch for. For ELF file, you might want to watch for ELF error because something might not actually be an ELF file. And also, One thing to watch for is open an ELF file returning none. None is the Python equivalent of null. So it's saying something went wrong. I can't give you anything back because I don't know what to give you. So I've given you a little debugging, little piece of Python code for debugging. It's called debug.py. You can use that if you want. The way you use it is just like you see right here. You say front, you put this debug.py in the same folder as your program. And then you say from debug import error debug, and if you want the all uppercase debug. How does this work? Well, it's another little simple piece of code. And you can see that here in main, I have a debug statement in main. And I can use F strings, whatever I want in here, it's fine. And then if I find the string Fred in capital debug, I print Fred. And then I have error, nothing defined here yet, and a debug down here. So here's what that looks like. If I just run this with nothing, then it'll come here, hit this error, and I'll get an error message. Nothing defined here yet. Now if I set right out in the in the shell, if I set debug equal to Fred, then that's going to get trapped right here, and it's going to print out Fred. And sure enough, that's what it does. And of course, it still hits the error. But I can also say debug equal debug, comma, Fred. And when I do that, I've enabled debug. This enables debugging. Now debugging is enabled. I get all the debug messages. So the simplest way to use this is just to have the debug flag in there, which turns the debugging messages on. A more complicated way to use it is to use it to pass information into your program, which can let your program do different things. It's up to you how you want to use it. How you want to use it, it's fine with me. Some hints. I would try to do the disassembly of the IPython prompt, and I would poke around and see what's in there. I would check for and handle error cases, definitely. And how did I format the number that way? You saw this number. How did I get that? You can do it this way. F string 0x, and then here's my little open and closing curly braces, and inside that I have an address. This will be a variable address, colon 016x. This looks for all the world like a printf format, right? And they're very similar. So this is the variable colon and then the format for it. And there you go. Some imports you're going to need just to get you started. You're going to need sys so that you can get to the arguments, the command line arguments. You're going to need elf file and elf error. You're going to need the things we saw earlier, CS, because you're going to need to be creating a disassembler. And you'll need x86 and 64 because you're doing 64-bit x86. And you may want debug and error out of my debug package. It's up to you. Use Pylint. It will help. And that's it. I hope to see you all on Tuesday. Hopefully I will not be sick and I won't be called away at the last minute to go do something else. And I'll actually be there in class. And you will have to suffer through me in person. Take care.